Hi, and welcome back. So in the past couple of videos, we've been talking a lot about dimensional analysis, and I've been talking about it in the capacity of how you can use dimensional analysis to solve sort of simple problems, and as we progress through the playlist, we'll use it to solve more and more complex problems. But all the previous, I guess, dimensional analysis examples we've really had haven't really had that much to do with chemistry. They've all been converting. One was about if we run at a speed of 6.5 miles per hour for 45 minutes, how many meters do we go? And I think that was one of the problems. And so we haven't been doing a chemistry related dimensional analysis problem. So what I wanted to do in this video was I wanted to give you a problem that we're going to solve. We're going to use dimensional analysis completely to solve it, and it's going to actually seem like chemistry. So what we're going to do is we're again going to take a look at copper on the periodic table, and we're going to once again go back to our old example of the penny. And so what we are going to try to figure out is based on the mass of a penny, and a penny has a mass of about, and we're going to say penny. This is two significant figures, that a penny has a mass of 2.5 grams. And this is a number with two significant figures. So we're going to say that this penny has a mass of 2.5 grams, and we want to know how many atoms are in this penny based on this mass. So we're going to do this. I guess if you also remember from the video, or from the past videos, I was saying that you can start with information you know and then get to, I guess, the information that you're looking for, or you can start with the information you're looking for and then get to where you and then eventually throw in all of the information that you eventually that you have for the problem. And in the last video, I think I might have done sort of a confusing example where we started with what we wanted to get. So in this video, I'm going to start with what we're looking for. I'm going to start with atoms. So I'm going to say that atoms of copper, and it does matter. So because we're talking about mass, so we could say atoms of Cu, which is the symbol for copper. Atoms of copper is going to be equal to, and let's start out with the mass of a copper atom. So a copper atom, and remember that this is on average. This is the average atomic mass. If you took all the different isotopes of carbon and you gave or not of carbon, of copper, and you had a weighted average of how much the mass of each of those atoms was, you would get this number, which is 63.546 atomic mass units. So we can say, and I'll just scroll down so I can still see that. So we can say that every one atom of copper, and this is on the top of my fraction now because this is the unit that I want to get, and the unit on the bottom is going to cancel out, that every one atom of copper is going to have a mass of 63.546 atomic mass units. So that's 63.546 AMU. So now what we have to do is we have to convert atomic mass units to grams, because that's what we know about this penny, that this penny has a mass. This penny has a mass of 2.5 grams. So we have to be able to convert atomic mass units to grams. So we can say that every one atomic mass unit, and we've set this up so that our units will cancel, that every one atomic mass unit is going to be equal to 1.6605 times 10 to the minus 24 grams. And again, this is, I think I've given you this number before, previously in the playlist. This is probably one of maybe two videos where you'll ever actually need to know this number. It's good to have it written down somewhere in your book that one atomic mass unit is equal to 1.66 times 10 to the minus 24 grams, or I've written it out to a few more digits here, but it's maybe good to have this written down. You're generally not going to be using this figure a whole lot, but here we are going to be using it. And then the very last thing, what's the very last thing we have to put into our conversion factor? So now we've got AMU, cancel with AMU. We just have to put in essentially the information that we're given, that the mass of a penny is going to be 2.5 grams. So now we're ready to just go ahead and put this all into our calculator. And I'm going to see, hopefully this calculator will actually do this conversion. I think it should actually be okay. So let's start out on, actually, you know what? Let's start out, we'll start out with 2.5. So we say that we have 2.5, and then we're going to divide that. I'm going to divide by just this part of my denominator. So divide by 1.6605. And it's important to remind yourself that I can do that, right? Because this is just, essentially I'm multiplying something, 1.6605, times 10 to the minus 24th. So I could even say, and this is actually what I'm going to do, I'm going to say that dividing by 10 to the minus 24th, that's the same as if I said, that's the same as multiplying by 10 to the positive 24th, right? So I'm actually going to, let me actually explain that real quick, just in case you haven't seen that before. So I'm going to essentially, and also because this is pretty messy up here, but essentially what I'm doing is, so if we start with, I say, 1 atom over 63.546 AMU multiplied by 1 AMU, and we've got, on the bottom of our expression here, we've got this number, 1.6605, 1.6605, and then times 10 to the minus 24th grams. I can just say, because this is a negative exponent, I can make that a positive exponent and multiply it up here, right? Times 10 to the 24th. So I could say that 10 to the 24th atomic mass units is going to be equal to 1.6605 grams, right? So I'm able to do that. This is just hopefully just algebra. If you didn't understand that, definitely go and check out the Khan Academy's videos on algebra and rules of exponents. And so then I'm going to multiply times 2.5 grams. And so now I'm going to get the calculator back out. And actually, you know what? I'm going to start this over. So I'm going to say 2.5, so 2.5, and then I'm going to divide by 1.6605. So divide by 1.6605. And then I'm actually not even going to factor in this 10 to the 24th. I'm just going to divide by 63.546. So divide by 63.546. And then I've got this number. And I could raise this to 10 to the 24th, or else I could just start writing this out. So I could just say that we've got two significant figures here that we're dealing with. So I could just go ahead and write out that we've got 0.024 times 10 to the 24th, right? Because that's all we're doing, is we would multiply it times 10 to the 24th. So let me just go ahead and write that down. So we have our final answer, or we're close to our final answer. We're not quite there yet. It's going to be 0. I think it's 0.24. I'll check again in a sec. 0.24. One sec. Yeah, that's it. 0.024 because we had two significant figures. And then we're going to multiply that times 10 to the 24th. So times 10 to the 24th. And this is how many atoms. This is how many atoms of copper are in this entire penny. And what's the last thing we can do just to make this look maybe a little bit nicer? Well, we can move this decimal point over, right? We can move it over 2 spots. So we can move it to there. And then what are we going to do to our exponent? Well, we're going to decrement it by 2, right? So we can say that this is going to be the same exact thing as 2.4, and we move the decimal place over 1 spaces, 2 spaces. So we're going to say this is times 24 times 10 to the 24th minus 2. So we would say times 10 to the 22nd. Atoms of copper. And this would be our final answer for how many atoms of copper we have in this penny based on the mass. Hopefully that last part wasn't confusing you too much, where I was doing the stuff with the exponents, and I also showed you that I didn't, and maybe I'll make another video on this about how I didn't have to even put in this exponent. I know it was part of scientific notation, but I didn't have to put this exponent into my calculator. I just put into the calculator this number, and this number, and then it was pretty easy to figure out this 10 to the 24th and where that would fit in based on the result that I got out of the calculator from putting in these 3 numbers. Hopefully that made sense to you. If it didn't, I'd say definitely go check out the Khan Academy's videos on rules of exponents and stuff like that, and algebra. I'll probably do some more examples, and maybe some more examples where I'll try to clarify that a little bit for what I did right there at the end. But anyway, this is the answer to our problem. We have 2.4 times 10 to the 22nd atoms of copper in this penny. And we figured it all out just using dimensional analysis. So anyway, thanks for watching, and I'll see you in a future video.